Welcome to Safi Tech here at SMT AI. I'm joined by Ian Tevis, who's the Chief Technology Officer. Welcome, Ian.
Thank you. It's good to be here.
Yeah. Now, you've come out with a really unique new product which addresses the low temperature solder business. This is an industry that's been growing quite a lot. There's a lot of interest in low temp, but you've taken a very unique approach to it with a product called No Heat SAC 305. It's a challenging name right off the bat, I can tell you, but tell us a bit about No Heat SAC 305.
Sure. So we're a startup company, and we are making a material that takes a molten metal like SAC 305, and we encapsulate it so that you can have a micro powder that you can use and apply a solder material at ambient temperatures, so you can get a solid joint made from that solder metal with no heat impact whatsoever.
It's incredible. I mean, the ramifications of that is enormous. I mean, taking heat out of the process. But let's talk a bit about the product itself first of all. So it's the SAC 305. It's encapsulated in some oxide layer and coating. Can you talk a little bit about what that is?
Sure. So we use the native oxide of the metal as the shell. And it has also a very thin organic layer on it. And so this shell is the magic that keeps this molten metal liquid at very low temperatures. So the microcapsules are coated in the native oxide, and then we have the organic layer. So what that allows you to do is then either mechanically break open the shell, or you can dissolve it just like regular solder processing. You have a chemical flux, dissolves those oxide. Same way, releases the liquid metal, it flows out and then turns solid within a few seconds.
So you can keep that liquid, that SAC metal liquidus at ambient temperatures by encapsulating it in these shells.
So we have a prototype version of SAC 305 now, and in 2020 we'll have available samples of that. So we're working to get it down to as low as ambient. But we already have pretty low temperature liquidus for the SAC 305 that we're working on.
How low?
Lower than the processing temperature for bismuth tin today.
Okay. So you can't put a number on it, but it's significantly lower.
Not going to put a number on it today. Yeah.
So you've got some cute examples here. I see of actually printing the process on a rose there. Oh, yeah. Tell us a bit about that.
Sure. With the rose, a very delicate organic substrate, we were able to print on the rose, which is a nice hydrophobic surface, and then we use a chemical flux to dissolve the shell, and you get a nice conductive pattern right on the rose petal without any damage whatsoever to that rose.
Really cool. So, as I said earlier, the ramifications are enormous. Companies are going to by using this, would save a fortune in energy. You wouldn't need huge reflow ovens in the assembly line. I mean, it really is a game changer, this.
Right, with the reflow ovens, they do take up a lot of space too, and so you can start to put more things in that footprint. Beside the energy, you get stackable benefits of that no heat. The substrates, the components, the energy in the reflow process, the throughput, all of that starts to come, all these added benefits from taking out that heat from the process.
So, as you said at the beginning, you're a startup, I believe, out of the University of Iowa?
Iowa State University.
Iowa State University, okay.
So close. Iowa State University.
Yeah.
Yep.
So what is your plan on how to take this to market?
So we are a startup, and we are making this brand new new material. So we're looking here at the SMTA International for partners to complete the manufacturing process. So we have new material, and we want to find the right equipment and the right process to create the complete solution and bring it to the OEMs at the end.
So what sort of equipment are you looking for? I mean, you're looking for something like a sintering system to break the shell, or what is it? How are you planning to do this?
So we're looking for ways of printing the material, also for applying our chemical flux on it, and then pick and place on the end. So our idea is that we'd print it in a normal screen printing process, and then we'd apply a chemical flux to the shells on the board itself, and then while the flux is acting, bring in pick and place components and push that down, and then squeeze out voids while getting that nice no heat solder connection at the end.
Okay, interesting. Well, it's a completely different approach, and I've got to say thank you for sharing it with us today.
Yeah, no problem. Thanks for having us.